Hello everybody, my name is Sebastian Goldt, and in this video I'm going to present you our MSML paper, The Gaussian Equivalence of Generative Models. This is joint work that was done together with Bruno Loureiro, Galen, Reeves, Florent, Krzakala, Marc, Mezard, and Lenka, Zdeborova. The starting point of this work was the observation that the datasets that we care about in machine learning contain a lot of structure, be they written text, images, or games of Go. And indeed, neural networks are very good at extracting that structure and using it to make predictions. But from a theoretical point of view, the way they do that, this process of feature learning, is very poorly understood. So the goal of our work was to make a step forward in that direction. Our work is based on ideas from statistical physics. And in statistical physics, the way to go about data structure is to model it using a teacher-student setup. This goes back all the way to Galen and Derrida and to works in the late 80s, and the idea very basically is to generate a data set by first drawing a set of IID Gaussian vectors, which will be the inputs, and then the label of these inputs are generated by a random neural network called the teacher. Here we're going to use two-layer neural networks with M hidden nodes. One then chooses a loss, in this case the quadratic loss, and trains another two-layer network called the student, either using stochastic gradient descent or empirical risk minimization. In any case, the goal of the analysis is to track the test error of the student, or in this case, the predictive mean squared error, which is just the squared loss averaged over the full data distribution. Now, before we go into our paper, it's useful to remind ourselves how the analysis in this vanilla teacher-student setup works. And it works by invoking something that we'll call the Gaussian equivalence property. So again, the goal here is to compute the mean squared error at all times, and for the vanilla teacher-student setup that I just showed you with ID inputs x, the test error can be written like this, where I've written out the teacher and the student explicitly, so V are the second layer weights, W the first layer weights, and G is the nonlinear activation function. So this is the student with K neurons, the teacher with M neurons, and we take the average, the high dimensional average over the inputs x. Now, to do that average, one useful thing to note is that the input actually only intervenes as a dot product with the first layer weights of the student and the teacher. We're going to call these dot products the local fields or pre-activations, lambda and nu. Now, because the inputs only enter this expression via these local fields, we can replace the high dimensional average over x with a lower dimensional average over the lambda and the nu variables. And this is a lower dimensional average because we look at this problem in the limit where the input dimension goes to infinity, but we keep the number of neurons in the hidden layer of both the teacher and the student of order 1. Now, these local fields are the key random variables for the analysis, both of online learning or of stochastic gradient descent, and for the replica analysis that you need to do in the batch case. So we really want to understand the statistics of these local fields. And in the teacher-student setup, they're actually quite easy. The inputs are element-wise IID, so their correlation is just the delta function. So lambda and nu are actually jointly Gaussian. We're going to call this the Gaussian equivalence property. And because they're Gaussian, their distribution can be fully described by the first two moments, and so assuming the mean of the inputs is 0, the prediction mean squared error can be written as a function of only the second moments of lambda and nu, which we're going to call Q R and T. Let's keep this in mind because it's going to be important for the analysis later. Now, this vanilla teacher-student setup has still some defaults. For example, the inputs, Gaussian IID vectors, they're not very structured, right? And so there's still quite a big gap to the images that we usually train neural networks on. And this is where the hidden manifold model comes into place. And this is the model that we analyze in our paper. The goal of the hidden manifold model is to give a slightly more realistic setup for data, for the analysis. And the idea is to start with a latent variable, C, which is a random Gaussian vector, and then to feed that latent variable through a generative neural network, again, or normalizing flow, to obtain a nice input x like this image of a dog. The label is obtained by having a teacher act directly on the latent variable C. And the idea here is that the label of this image of a dog, it shouldn't depend on the value of each and every pixel, right? But it should depend on some higher level features which might be more appropriately modeled by this latent variable C. This is how you generate data, and then once you have that data, you can apply a static feature map, and then importantly, you can train a neural network on those features. And this is what is learned from data, the weights of this network. The contributions that we make in our paper are threefold. we first prove a Gaussian equivalence theorem, or GET, which gives rigorous conditions under which we can analyze learning when data is coming from single layer generators. And in the second part, we then use this GET to derive dynamical equations that describe the dynamics of neural networks trained using stochastic gradient descent, and to do a replica analysis of random feature regression, again when data is coming from this hidden manifold model. Now let's take these things one by one, starting with the Gaussian equivalence theorem. So the setup here is that we're looking at a fully connected single layer generator, which we're going to call G, and it's got a weight matrix A, a nonlinearity sigma, and the teacher is again acting on the latent variable C. Now, if you wanted to repeat the analysis that I just showed you from the vanilla teacher-student setup, there are two complications that arise now. The first is that the inputs now have a non-trivial correlation matrix omega, and the second is that the teacher and the student don't act in the same vector spaces anymore. Okay, so the teacher now acts directly on the latent variable while the student acts on the feature. Now, a priori, it's not at all clear that lambda and nu are Gaussian. The x's certainly aren't Gaussian anymore. They have some distribution, so it's not clear if the lambda and nu's are still Gaussian. What the GET tells you, though, is that they're still sometimes Gaussian. More precisely, what the theorem tells you is that if you let P be the distribution of the pair lambda and nu, the real distribution, and you compare that distribution to a distribution P hat, which is a Gaussian distribution with the same first and second moments, then you can introduce a distance between distributions. In our case, it's a variation of the total variation distance. And you can show that that distance is bounded by this expression that I'm showing here. And in particular, this distance will go to 0 as n, the input dimension, goes to infinity. Now, to gain a little bit of intuition, let's look a bit more closely at the different terms that intervene in this bound. And we will see that there's the student weights, there's a product of teacher and generator weights, and the student weights enter via multiplication with two matrices M1 and M2, which are related to the input correlations. And these two terms are really important because they give you the basic intuition of our result. So imagine you have some inputs x, and you look at the covariance matrix. There will be some dominant directions here, which are the leading eigenvectors of that covariance matrix. And now what this GET tells you is that as long as the weights W don't align too much with the dominant directions of the covariance matrix, the local fields lambda and nu will still be jointly Gaussian. Right? This is a result that holds for any given weight matrix. So any given weight matrix for the student, any given weight matrix for the teacher, for the generator, you can plug those in and see what the scalings are. And there is quite a bit of related work and quite a bit of interest at the moment in Gaussian equivalence theorems. We discuss related work quite at length in the paper. Here let me just highlight three strands of similar results. One is work on Gaussian approximations in wide network limits. Those rely on random matrix theory and thus on random weights. And so the key difference here is that our result holds for any given weight matrix. There's some nice series of work by May and Montanari and the group of Romain Couillet, which introduced related equivalent Gaussian models for integrals with respect to spectral densities. This is important if you want to do linear regression on random features, for example. Here the key difference is that we're looking at these two-layer neural networks with these nonlinearities in the middle. And finally, there's a large body in statistics of work on low-dimensional projections of high-dimensional data being Gaussian. And here, a key aspect of our proof compared to these works is that we quantify how Gaussian they look like by really giving this very explicit bound. Now, let's put this GET into use. And the first application that we show in the paper is to calculate dynamical equations or to derive dynamical equations which describe the dynamics of two-layer neural networks when they're trained using stochastic gradient descent. And the goal, more precisely here, is to derive a set of closed equations that describe the dynamics of these order parameters, these second moments of the local fields Q and R. Now, in the vanilla teacher-student case, this has been done in some seminal papers by Sarton Sola and Biel and Riegler in the mid-90s. And so our job here was to extend this analysis to this hidden manifold model that I showed you before. And it even turns out that this can be done. And the trick is to rewrite these order parameters Q and R as integrals over a density, small q, small r. And these densities are parameterized by the spectral density of the covariance matrix. And one can then derive equations of motions for these small q's, small r's, and we do that in the paper. The key point here is that, remarkably, the generator of your inputs only appears via two covariance matrices, the input-input correlations and the input latent variable correlations. And so this means that a priori you could use these for much more complicated generators than just the single layer generator where we have the rigorous Gaussian equivalence theorem. And so this is what we did, because experiments are cheap and easy to do. So we used the pre-trained convolutional GAN and the normalizing flow, so some really powerful generative models to generate the inputs. They're deep models. We pre-trained them on Cypher 10. You can see some Cypher 10 images here and some samples from the real MVP. And then we trained a neural network on this data, a two-layer neural network, and we integrated the equations of motions that I just showed you, and we compared the two. And as you can see here, the agreement is very good. So on the top left, we show the prediction mean squared error as a function of time, and the other three plots show different order parameters, also as a function of time, with crosses being simulations and lines being results from integrating these equations of motions. So this is a first hint at the fact that this Gaussian equivalence theorem that we have rigorously in the single layer case holds much more broadly, in this case for deep generative models with pre-trained weights. And this is the point we're going to come back to at the end. We also use this to look at a random features logistic regression on a finite data set. So this is a different setup in the sense that it requires a finite data set. You do batch gradient descent, so it requires different methods. In this case, the replica method from statistical physics. And this calculation then gives you the generalization error as a function of the sample complexity, so as a function of the number of samples that you have in your data set. And here we show this again for inputs that were pre-drawn, that were drawn from a pre-trained generative model, the convolutional GAN in this case, and we can see again that for different ratio of random features to input dimension, the agreement between theory and experiment is very good. So this is another case where the Gaussian equivalence seems to hold beyond the limits where we could establish it rigorously. Now, the full details of these calculations and of these derivations can be found in the paper. Let me finish this video with some perspectives. So we saw that this hidden manifold model with its complicated inputs can be subsumed in a Gaussian model for data, in a Gaussian model for these local pre-activations. In the paper, we focus on II teachers that are random, with random weights, but we can also extend this to pre-trained teachers. And this then gives us an additional covariance matrix, which we denote psi, which is the covariance of the needs with each other. And for this more general Gaussian model, we can rigorously establish the convergence of the empirical risk, and we did this in some follow-up work. The proof was led by Cédric Jabelot, and Hugo Q was also working on the paper. And there's also a complementary proof of the risk of convergence for such a Gaussian model that was given by Hugh and Liu a bit before that at the end of last year. And the theorem looks a bit like this. So a lot of what I've said here, which were sort of conjectures from statistical physics, can be put on a rigorous footing. And like I said, it's quite surprising that this simple Gaussian model, if you will, is valid in quite a lot of cases where the inputs a priori are not Gaussian, where the generative model is pre-trained, where even the teacher is pre-trained, where you have a static feature map like some random features or some scattering transforms. So you can get more and more realistic learning curves from analyzing the simple Gaussian model. And so this, I think, is in itself quite a remarkable result, or quite a remarkable fact. And this is something that we're still looking at. So the two big goals, I think, here are to establish the limits of this Gaussian equivalence. So how far can we push this? How realistic can our learning rules get and our generalization plots get? And of course, the second big question is can we go beyond these Gaussian models of data? Can we understand how higher order moments, higher order cumulants of data impact learning in neural networks? Thank you very much for your attention.